Again, thank you for joining us. What I'm going to try to do today is go through the basics of dynamic light scattering and along the way indicate where the Microtrac way is implemented. The basics of dynamic light scattering stem from the physical phenomena of Brownian motion. All suspensions of particles have a thermal interaction with the media that they're in, and that results in particles being in a constant motion. The distribution of this motion, if it's thought of in terms of velocities, give a determination of the particle size. And dynamic light scattering gets its name because if you irradiate a suspension with a laser beam, that light will scatter from the particles, and the fact that they're moving will impart information onto the light beam and the collected scattered light. A basic setup for the optical detection of the particle motion is shown here, where a laser beam is focused into a particle suspension at a point that is considered the viewing volume. Another in the scatter direction, which can be picked at at any angle. Another optical system is assembled where the scattered light is collected from that scatter volume and focused to a photodetector. The enlargement there shows the focal point of the laser with a random scattering of light. The angular direction that the photodetector is set up at will pick off just that angle. If we look at the photodetector output, it has a general intensity that is constant over time at a DC level. In the left-hand plot, you see essentially the DC intensity with a little bit of ripples showing through. If the DC is filtered out and we look at the AC component, intensity versus time signal becomes what looks like a noise. But the noise is the result of the particles moving and interacting with the optical beam, and it's through the analysis of that noise spectrum that particle size distribution can be extracted. There are essentially two ways to extract this information. One is to irradiate the sample with the incident light, collect the scatter at a given angle, and in the same path, introduce a portion of the incident light that will be delivered to the photodetector at the same point that the incident light, the scattered light, is introduced. This is called reference beating. Beating because these two beams will now interfere with each other and give us a signal that has the information of the moving particles. The other configuration does not use a reference beam, but it depends upon the fact that the scatter light can mix with itself and give us a beat signal. We have been using reference beating. That was initially that has been called heterodyne detection, as opposed to the self-beating, which has been called homodyne beating. That terminology is changing to what I have indicated here in a recent ISO revision of the dynamic light scattering standard. So we're going to continue using we'll use the newer description. The reference beating we have found to be superior to self-beating in the fact that you get an optical signal that is 100 to 1,000,000 times stronger of the noise content of the signal. This comes about because the reference beam can be that much higher in intensity than the scattered light. Scattered light is usually very low intensity. So if you're doing reference beating, then you're working with a much higher signal, and that leads to a number of advantages. The biggest advantage that we've found is that you can, with simple and reliable photodiode, photodetector, and laser diode system, you can cover a very wide range of sample concentration. Shown here is a common 100 nanometer, 125 nanometer silica particle running from a few percent concentration down to part per million concentration, where the measured size is very, very repeatable and constant, independent of the concentration. The way we implement the reference technique is using a simple optical fiber to gradient index lens system that creates an image of the fiber at a point in front of the lens. These components are very simple cylindrical components, and they can be assembled in a holder that is then the alignment is then frozen in place. The alignment being just the two surfaces are brought together and held there in a sleeve. That becomes our controlled reference probe. That is then used in a probe tip, where that focal point is slid into another sleeve that has a window in the front, and the focus is brought to the accurately to the surface that is the interface with the particle suspension. So this focus is then accurately brought in, and that is frozen in place. So the probe becomes an optical bench where all this action takes place at the suspension interface. So we look at that in a little bit more detail. The focal point is at the interface, provides the introduction of the laser beam into the suspension, and the point where the scattered light is collected and sent back into the fiber. This is 180-degree scattering, and the return light is in the same direction, but 180 degrees out of the delivered light. The important aspect of the interface is that there is also a reflected beam. Regular optics tells us that when there's a index of refraction difference between one media and another, that interface will have a reflected component. In our case, we use a sapphire, generally use a sapphire window on the probe, and the suspension is generally a water type of fluid, so that there is a large index of refraction difference. And in fact, with that combination, you get about a 2% reflection of the laser input is reflected back into the fiber. This combination of focusing at the interface and using the back reflection gives us an added benefit in trying to detect the dynamic light scattering, in that the scattered light is collected over a limited thickness of sample, and that limit means that we're able to measure the scattering without penetrating a large thickness of sample. If you were to use say a cuvette and have laser light going in and out of it at a larger angle, then you could have path lengths the order of a centimeter, and at high concentration of sample, the attenuation of the laser beam, both the introduced laser light and the collected scattered light gets attenuated, and in fact, you would be limited to, as an example, a simple 100 nanometer poly or silica material would have an attenuation that would be orders of magnitude if you were going through a centimeter of sample, whereas going through just the 50 micron viewing volume in the focused at the interface execution would be just a minimal amount of attenuation. So that allows for the measurement up to 30–40% volume. You're getting, at that point, it's very close to the theoretical packing of a sphere in a fluid, and all motion, Brownian motion, would cease when the particles are in full contact. So that extends the concentration range up another order of magnitude from that graph that I showed you at the beginning. That leads us to how this data is analyzed. We measure then, with the system I've described, we measure a noise-like signal that is the output of the photodetector. This is all, we get the noise signal by doing a DC filtering of the base intensity, and we're left with the noise signal. Now that noise signal has a content in it that represents the velocity distribution of the particles. And it's from that distribution that we extract the particle size. So the first process that we go through is to convert the noise signal into a power spectrum. In other words, measure the frequency content of that noise signal and create a power spectrum, which is shown on the right. That has the characteristic of what's called a Lorentzian function as a function of frequency. So the power spectrum can be thought of as buckets of frequency range. So in a linear power spectrum, you have equal size buckets. And you can see from these plots here that are the response of different particle sizes, that when you have very small particles, the frequency is spread out over a very wide range of up to the maximum frequency that we're analyzing. As you go up in size, the frequency content is compressed more towards the low frequency end. The picture of light scattered from moving particles can be thought of in terms of a frequency shift imparted to the scattered light due to the fact that it is being scattered from a moving object, and a Doppler shifted frequency is imparted. When we mix it then with the reference beam, you have a base intensity, which is the DC part, but you also have an AC part, which is the Doppler shift that was imparted on that scattering event. And then this is summed up over all the particles that are being measured. And so the resulting distribution of frequencies says that the smaller particles are moving more rapidly and have a higher average velocity and therefore a higher average frequency shift. And then as you go up in size, that frequency shift gets smaller and smaller as the particles move slower and slower. Now, an important part of our analysis takes this processed noise data, processed into a power spectrum, and groups the channels which are linear in the top graph into channels that have a logarithmic progression. Now, the simple way of looking at it is that in the top graph, each one of those frequency buckets is the same size. In the lower graph, the frequency bucket starts at a small size and then it's progressively increased so that each channel is wider by a factor than the one before it, so that we can compress the data that takes tens of thousands of points into data that is shown in here we've got 54, but it extends out to close to 80 channels. And the important characteristic that grouping does for us is that the power spectrum now looks like a symmetric bell-shaped curve that shifts just in center frequency with size. So the three representative power spectrums in linear space change shape, but if they're grouped in this logarithmic progression, the shape is the same for all sizes, and it just shifts on this channel scale. Each one of those channels has a center frequency that is in the logarithmic progression. That has very important ramifications when you go to analyzing an actual measured power spectrum. The example shown here is mixing a sample with a small mode and a large mode. So these are two narrow modes mixed together, and the power spectrum is shown of the combination. And the 120 nanometer portion and the 15 nanometer portion are mixed together. And to analyze that, to get our particle size distribution, we can go through an iterative iterative process that ends up with a best fit of a particle size distribution to determine that power spectrum. And it's because we have been looking at it in this logarithmic space, the calculation of the combined power spectrum is simply a linear combination of the individual particle power spectrums weighted by their signal intensity, which is concentration and scattering efficiency. So with this bimode here, the contribution of the 15 nanometer particle is shown as a distortion of the 120 nanometer spectrum, and that addition then is what gives us the ability to calculate a mode at 15 nanometers and a mode at 120. The process is relatively simple. Since we can calculate a power spectrum from a size distribution by just using the linear combination, that step can be done by starting with an estimated size distribution and calculating what the power spectrum would be. That calculated power spectrum is then compared with what's measured. And since the estimated distribution is very different from the final, there'll be a large error in the difference between what we calculate and what we measure. That difference is then used to correct the estimated distribution a small amount, and the step is then iterated until the error between what we calculate for a power spectrum and what we measure is brought to a minimum. And the data shown here shows that the power spectrum of the mixed mode will result in a particle size distribution that represents the two sizes of the particles and the relative concentration of the two particles. This is in a form that is using just the signal level that is generated. That can be corrected to give you actual volume ratio with the known scattering efficiency of that size particle. So that is the story of the Microtrac size analysis using dynamic light scattering and the controlled reference technique. It allows us to take these mixed signals at different concentrations and different samples and get a full particle size distribution from the bottom of the range to the top of the range, a nanometer to 6.5 microns. The Microtrac way is using the measurement technology of dynamic light scattering. We have an optical configuration that uses reference beating and creates the reference through the controlled reference probe. we process the time data into a frequency power spectrum and then group it into log channels. That gives us a distribution determining analysis that is a very straightforward iterative convolution with error minimization. The instrument utilizes the control reference probe and comes in a variety of configurations that run from a built-in probe into a sample cell, a cuvette where the cell is removable, or an external probe where you can provide your own sampling. Let me turn this back over to Jason. He's got some final remarks, and we'll continue.
All right, thank you, Dr. Fruit. So just to introduce our DLS product line. As Dr. Fruit mentioned, we can go from 0.8 nanometers to 6,500, and we can measure materials with a concentration up to 40%. On the left is the Nanotrac Wave that features a Teflon cell, sample volume of about 250 microliters. That also features a Peltier-controlled temperature device, so you could either heat or cool your material and see how that affects the particle size. In addition to, we have a flow cell option if you are interested in performing titration. In the middle, we have the NanoFlex. That's the external probe model. If you turn it up, we don't recommend this, but if you turn it upside down for demonstration purposes, all you need is just a tiny drop to register a reading for the analysis. You could pop that into a vessel. It's ideal for in situ measurement. Simply dip and go, wipe off. Very ideal for quality control. Also, the probe has multiple lengths, so we can customize that for you as well. And then on the right, the Nanotrac Wave Q, which is our cuvette version of our DLS analyzer. One of the things that's unique about our system is we have cuvette error detection alerts, which basically says there's either a smudge or your cuvette's not inserted properly, and it will not let you make a measurement until you fix the orientation of your cuvette. It also comes in 4 compatible cuvettes, a 1,000 microliter macro volume, which is made out of plastic, a 1,000 microliter glass cuvette, a semi-micro that's 300 microliters that's made out of plastic, and then our 50 microliter cuvette. So some next steps. As we mentioned, thank you for attending this presentation. We would invite you to send some samples for complementary analysis if you would like to see the Microtrac way in person or some data of your material. Please email me, jason.nova@microtrac.com, and we can make arrangements for you. We also could do a virtual demo. You could send us samples and we could walk you through what the data would look like. As well, we could also come to your facility and demo it live if you are interested as well with one of our regional technicians.